Okay. So today I'm going to provide a brief introduction to some content from the Highway Safety Manual that will build upon a lot of the stuff we've covered in the last few lectures as we've talked about different evaluation methods culminating in the empirical base. And so after today, you should be able to estimate safety performance functions, also to develop crash modification factors or functions, and then generally speaking, apply the methods that are used for predictive analyses as per the Highway Safety Manual, okay? And so I honestly can't recall how much we talked about this during maybe the first week or so of class, but have you guys worked with the HSM at all? Okay. Have you seen it at all? I don't know if that was introduced in 341 or okay. So it basically they're currently in the process of developing the second edition, and so this was many years of research work basically culminated in the first edition, which was published in 2010. There was a supplement in 2014 that covered a few additional facility types. And then there's been a range of additional research since then that's led to some of the updates that'll be in progress moving towards the second edition. And so it's basically the safety analog to the highway capacity manual. I'm gonna do a very quick tangent here. Completely unrelated to class stuff. Have you guys been informed about the ITE traffic bowl stuff? Okay. Are you guys planning to participate again?
We were both going to abstain, and Shakir said he'd rather have people that weren't graduating this year because he wants new people doing it.
Okay. What was huh.
I think we
uh,
both volunteered and said if no one else is available, we'll do it. But I guess I don't want to speak for Travis, obviously.
okay.
That's the same for me as well.
Okay. It just popped into my head randomly because we got to get our list of people in this week, and I know you guys were both on the team last year. So, okay. I will now pull it back into the lecture. Sorry. So like I said, the HSM is basically an analog to the Highway Capacity Manual. It's basically science-based. It builds upon a bunch of research studies that have been conducted nationally and provides basically some quantitative tools that can be used for safety management decisions. And so it was largely motivated by the fact that historically safety related work has been more reactive in nature, and so based on crash histories and things of that nature. And so with the introduction to the HSM, it's becoming a lot more data driven and quantitative in nature. And so to that end, we'll only get into parts of it because it's three volumes, and there's a ton of content, and so we'll at least provide a general overview to several of the different chapters that are particularly relevant there, and then some of the high level descriptions and methods and so forth that are applied. But it presents a lot of the stuff we've talked about already up to this point to varying degrees. So predicting the safety performance of a road facility, identifying or screening high risk locations. So like the network screening step that we've gone through a few examples of, estimating the effectiveness of a given countermeasure as well as the cost effectiveness. And so we'll talk about some of that a little bit more as we move through as well. But today we'll start talking generally. So when I use the term safety performance function or SPF, is that a familiar term to you guys? Okay, so basically it's a statistical model that relates how many crashes we'd expect to see at a given site with certain conditions, primarily traffic volume, roadway geometry, and then that information can be used, for example, if we're designing a facility and we're looking at different potential design decisions as to what the impacts would be. The highway capacity manual, as an example, we can quantify that reducing lane widths from 12 feet to 11 feet would reduce speeds by 1.9 miles per hour. And if you drop it down to 6 feet, or sorry, to 10 feet, it would reduce speeds by 6.6 miles per hour. we can come up with the same sorts of insights in terms of what some of those design decisions would be from a safety standpoint as well. And so that's what's driving a lot of what's been included in the highway safety manual. And then in addition to just prediction for those purposes, this is also very useful when we try to do evaluations of the effectiveness of different countermeasures, specifically as we look at the empirical Bayes method that we've talked about over the past few weeks. Okay. And so the general forms of these SPFs are basically as shown here. Now we're lagging a little bit behind where we'll get to this type of content in CE 849. But essentially the way these models are structured, they're going to take the form of a Poisson or a negative binomial model. And so in this case, we can use similar methods to what have been introduced for linear regression, with the big exception there being that we're essentially transforming our predictive, our dependent variable here. So instead of estimating a model for crashes as a linear function of predictors, we're basically estimating a linear model for the log of crashes as a linear function of predictors. And so, so when you look at this, we're actually, the way the models are presented, estimating the log of the number of crashes, and we had talked a little bit about this in 849, is not as particularly useful from a practical standpoint, because if I tell you there are going to be the log of 3.4 crashes or whatever the case may be, that's not a very meaningful number. And so the way these models are presented they've been transformed such that we're predicting the number of crashes at a site rather than the log of the number of crashes. And the primary implication there is that the linear function on the right-hand side that we typically see is now exponential in nature instead. Okay. So all we're doing, we've got the log of crashes as a linear function of these predictors, and then we exponentiate both sides, and this is the final form we arrive at. Okay. And the general form here is slightly different for road segments versus intersections. So if you think about the factors that would most directly influence the safety and the number of crashes at those given sites, the primary driver, and this is going to be true for any type of analysis we conduct where we're looking at site-specific crashes, is the strongest predictor for crashes is going to be what?
Volume.
Yeah. So volume is going to be the strongest driver. And so in the case of road segments, and this is an example for rural 2-lane, but we see this same general format for any type of segment as per the HSM. The exponential of A, so A here would be just our constant term as we would estimate in various other families of models. AADT here, you'll notice, is logged. And so an alternate way of writing the same expression, we could pull that AADT term out and we could raise it to the power B as an example. And so that's essentially an equivalent expression. And so what this B is basically telling us is the elasticity of crashes with respect to volume. And I don't know if you've heard that term elasticity within the context of economics or whatever the case may be, but it's basically telling us for a 1% change in traffic volume, that would be the corresponding percent change we would expect to see in crashes. Okay. So as an example, if B were equal to 1.0, that would mean that a 1% increase in volume would result in a 1% increase in crashes. If B was greater than 1, this would be very elastic in nature. So in that case, say if B was equal to 2, that would mean a 1% increase in crashes would result in it, or a 1% increase in volume would result in a 2% increase in crashes. And similarly, if that was less than 1, it would indicate that a 1% increase in volume would result in something less than a 1% increase. And so if we think about that, if we assume it's equal to 1, we just have a straight proportional relationship. If B is greater than 1, it starts to, and apologies, this isn't showing up correctly as I'm trying, it's trending upward. And then if it's less than 1, we have that effect where it's kind of tapering off at the top. Okay. hopefully my hands were going in the right directions there. And so in addition to volume, the other important factor to consider here is segment length, because the longer a segment, the more crashes you'd expect to see, all other things being equal. You'll notice that's also transformed here. We're taking the log of that length. And so similarly, that term can be pulled out of the equation. And so it would just be the length to that parameter C. In many instances, we'll basically constrain this parameter estimate to be equal to 1. And the reason for that is just empirically and hypothetically, it makes a lot of sense to kind of force that assumption into our model. So what we're basically saying there is if you double the segment length, you double the crashes. If you triple the segment length, you triple the crashes. And that seems to be a reasonable assumption, right? Now, there are some implications of that. So we could estimate a model and allow that to vary. But one of the concerns that arises there is oftentimes we've got a lot of really short road segments. And so the HSM provides recommendations as to minimum lengths for some of those segments. But what we'll tend to find, even if you meet those minimum length requirements, if the segments are too short, you can have some issues that arise there. And so essentially a workaround for that is we constrain this to be equal to 1. And in statistics, we refer to that as an offset term when we force that proportional relationship. And I'll show you guys in SPSS how we can introduce those offset terms. But like I said, we'll be getting to that in 849. Probably too late for it to be useful here. So I'll do some additional demos either later today, time permitting, or in the next week, and how we would estimate these models in SPSS. But in any case, that's how we would structure the segment equation. In the case of an intersection, obviously that length component goes away, but in this case, the primary determinants of crashes are going to be the traffic volumes of the major and minor roads. And so same general setup here. We're logging both of those volumes. And so an equivalent expression would be to pull each of those AADTs out of this equation, raise them to the B or C power. And then in practice, we could have additional predictor variables in here, so geometric characteristics, but these are basically simple forms that are introduced as essentially baseline conditions in the Highway Safety Manual. And so depending upon the facility type and the type of crash that we're interested in, the HSM provides a bunch of tabular summaries that show calibrated coefficients for A and B and C on different facility types. Okay, and we'll go through a subset of those today, but there's a very large number, too many to go through each of those individually here, but this will give you a sense of essentially how these are structured. Okay, and so like I said, these are developed so that they can be used for predictive purposes for quote unquote base conditions. And so as we're building our models, and this is also very analogous, if you recall in the Highway Capacity Manual, we would assume base conditions that would include 12-foot lanes, 6-foot shoulders, no interchanges in the case of freeways, no access points in the case of multi-lane highways or 2-lane highways, and so forth. And then we basically adjust from these base conditions when they don't apply. So we'll have factors that would either, in the case of the HCM, increase or decrease travel speeds, as the case may be, or increase or decrease volumes. And in our circumstance, we developed this base model that gives us a predicted number of crashes for some traffic volume range. We assume base conditions, and if those base conditions aren't met, we'll have crash modification factors that are introduced that functionally will basically shift these lines up or down, depending upon those variations from the base conditions tend to increase or decrease crashes. Okay. And so these are just a few examples from chapter 9 of the HSM, which focuses on rural 2-lane highways. And so as you can see here, we have different predictive functions for 3-leg stop control, 4-leg stop control, and 4-leg signalized intersections. Interestingly, the first edition did not have an SPF for three-leg signalized, and that was just basically the underlying research at the time that was published. There just wasn't sufficiently reliable and rigorous analysis there, but that's one of several that'll be updated in the second edition. And so as we look at these, back to my preceding point, these coefficients here, so the first number here, these A's, these are just the constant terms. And then these are capturing the relative influence of traffic volumes on the major and minor road respectively. And so in the case of the 3-leg stop control and 4-leg signalized intersections, you'll notice they're much more sensitive to volume on the major road as compared to volume on the minor road. Whereas in the case of 4-leg stop control, we've got nearly equivalent relationships between volume and crashes for each of those individual roads respectively. Okay. And so with these empirical models, we can take any given intersection, and if we have an estimate of the AADT on both of those roads, we can use this to come up with a baseline prediction that, again, is based on empirical research using data. In this case, I think these data were drawn from the states of Minnesota and Washington. And so the one point I should note here, and we won't get into this today, but hopefully we'll have time next week. So if we were to take these models that were developed in other states and apply them to Michigan, what we would probably tend to find is that they might systematically overestimate or underestimate crashes. Any idea why that might be the case?
Yes, different driving behavior by state could do it.
Yeah, so inherently there are going to be some differences between states. So if we estimated models in Minnesota versus Michigan, we'd probably see some differences here. Now, part of that might be due to driving behavior, although in the research literature, I haven't seen a lot of really compelling cases of extreme differences, at least across different geographic areas of the US. I think there are probably some more pronounced differences if we compare the US to other countries, for example, but that's one potential factor that could lead to some differences here. One big thing here in Michigan, 40% of our crashes involve what? Apologies for how ambiguously I set that up, but
Deer.
yeah, so roughly 40% of the crashes in any given year can involve deer in some instances. And so I get, depending on the facility type. And so that's a reason why we may see more crashes in Michigan than otherwise. Now, one workaround there is we could eliminate the animal involved crashes, and depending upon the chapter in the HSM, in some instances, they've estimated this just for non-animal crashes. In other cases, they've assumed certain average proportions of animal crashes, and so there are adjustments that can be made there, for example. But that'd be one difference. We might also see differences just in the way that roadways are designed. So here in Michigan, particularly intersections, less so in a rural case, obviously, but we've got Michigan left turns, right? And so if we were trying to compare the performance between urban intersections as per the HSM and what we see here in Michigan, we'd likely see some substantive differences there as well, because just the general patterns of design and so forth are different. And so I bring all this up because what's typically recommended is calibration for local conditions. And so we have had a series of projects for the Michigan DOT where we've taken these base models, applied them to Michigan data, and then we've estimated a calibration factor. And so all that calibration factor does essentially is it corrects for these constant terms, and it would shift these models up or down depending upon whether the state or the local area that we're calibrating to tends to experience fewer or more crashes than the base models. Okay. So again, we won't get into that in great detail today, but I just wanted to indicate that these aren't necessarily just plug and play per se, but okay. And so as we look at these models graphically, so this is just an example showing estimates of average annual crashes. Since we've got major and minor volumes, we could present these as like a three-dimensional planar surface, but generally it's easier if we just plot these versus AADT on the major road. And then each of these lines corresponds to certain levels of AADT on the minor road as an example, okay? And so you'll notice here, this specific case here, this is for single vehicle crashes on three-leg signalized intersections. Now, this kind of leads to one of the potential criticisms that I would have about the HSM generally, is that they get to very precise estimates of various subsets of crashes. And the degree in which, if you look at this, so if we're looking at a three-leg signalized intersection, and you think about the types of single vehicle crashes that would occur there, those would tend to be relatively rare events. And so the average frequencies here are ranging from 0.1 up to a maximum of just over half a crash or 0.6 crashes per year, okay? And so consequently, then we have a very large subset of models. And one of the other concerns I have with the Highway Safety Manual is that each chapter basically focuses on a different facility type. So chapter 9 is rural 2-lane. There are additional chapters on rural multi-lane and urban and suburban road segments. And so in each of those chapters, the functional forms of the models and the approaches that are presented are slightly different or significantly different in some cases from one another. And the reason for that is these were based on a variety of national research projects, many of which have been conducted through the NCHRP program over the years. And so they've basically just adopted whatever functional forms of those models were used as a part of the original research, okay? And so as an example, if we look at some of the methods in chapter 9, that's focused more on estimating total crashes. And then we would use tabular summaries of the proportion of all crashes at, say, a rural 4-leg stop-controlled intersection. We just use historical percentages of how many of those crashes would be angle versus left turn head-on versus rear end and so forth and so on. In chapter 12 here from the urban suburban arterial section, we're actually taking sophisticated models for each of those subsets. And chapter 11 takes a slightly different approach that is somewhat in between those two approaches. And subsequent research, including the 2014 supplement, has used an entirely different approach for some aspects. But I just want to give you a sense here. There's a wide range of flavors for these models. And so a lot of the stuff I'll be focusing on today and for our homework assignment will be more general in nature, and looking at total crashes as an example versus these very narrow subsets, okay? Because the narrower we slice this down, I mean, if we're trying to predict fractions of a crash per year, at some point you kind of get to diminishing returns largely with that. Now, with that being said, a lot of the content from the HSM has been used to develop decision support tools like spreadsheet tools and other interfaces where all you need to do is plug in the numbers. So it's not like it's particularly onerous for the agencies to adopt this. But here in Michigan, as an example, in those same projects I had referred to previously, we've estimated a series of Michigan-specific safety performance functions as well. And so like I said, there's a lot of variation in terms of how these are presented within and across facility types. And so if we look, no, drop. Okay, for real this time. And so if we look at how the HSM has been applied nationally, essentially a lot of states have all done things differently. So some states, and I can think Kansas and Virginia are two examples I'm familiar with, had projects that were focused on calibration. A number of other states have estimated their own state-specific functions. And a lot of it really varies depending upon how progressive those DOTs are, the availability of funding, and so forth and so on. Okay. And so, I guess I mixed up the chapter numbers. They're not 9, 10, and 11. They're 10, 11, and 12. My bad. But so chapter 10 is 2-lane rural SPFs. Chapter 11 is multi-lane rural SPFs. And then chapter 12 is urban arterial SPFs. And so, like I said, we had a series of companion projects here in Michigan where we also estimated SPFs for these different facility types. And so,
Arturas, I have a quick question.
Yeah.
I guess on slide 9, so 2 slides back, like, I guess, what is the significance, or what are you even going to do if you're predicting 0.2 crashes per year at a 3-leg signal location? Like, that's what, 1 crash every 5 years? Are you gonna, is it DO? I guess that would just be identified as a non-high risk location, or?
So, I mean, the way these are generally applied in practice would largely be for like network screening type applications and or evaluation projects. And so in the network screening example, I mean, a lot of states will still start by just ranking locations based on the number of crashes or the rate of crashes, even frankly speaking. But the more sophisticated, I guess sophisticated is the right word to use here. Some of those agencies will tend to use this information in combination with the crash information when they develop those ranked lists on an annual basis, for example. These are also playing a much larger role in design decisions, and this, I would say, has been a relatively recent evolution. So I know, like MDOT now, whenever they've got these safety projects, one of the requirements is that they would use the SPF to predict safety performance here. Now, I guess I didn't directly answer your question there, but as agencies try to forecast performance, in theory, we'd see more precision if we're using a series of, 10 different crash type specific models. It's probably arguable, whether that's going to give us a substantive improvement versus we just estimate a model for total crashes as an example. And so if we look at 3-leg signalized intersections, like single vehicles are just a very small proportion there. But I think if the way this is being considered, there are certain types of crashes subsets of crashes that would be impacted by certain types of countermeasures versus others. And so that's part of the advantage here, is that if we have these more detailed, precise models, we've got greater flexibility in trying to estimate the impacts of different types of design decisions or safety improvements that we would introduce. So as an example, I guess, if we were going through and retiming traffic signals, we'd probably see significant improvements in rear end collisions, and then less so in single vehicle and in some of the other cases here. And so, it's basically somewhat of a trade-off from the agency perspective, but we've tried in our prior MDOT projects to mirror the HSM to the extent practical, but if you look at some facility types, I mean, we're like rural segments where you might experience 1 crash per year, and we're trying to slice that down into like 5 to 10 subsets. I think it's very debatable whether you're getting a lot of value add from that necessarily. Now, with that being said, that's what a lot of agencies are doing, because the HSM, I don't mean to introduce religious analogies generally, but I was going to say it's like the Bible, kind of like agencies often just have kind of adopted it carte blanche without question for various reasons. And so I think that's a challenging area. So like if we had a chance to go back in a time machine, I would strongly encourage the AASHTO in developing the HSM to make it simpler, easier to apply, and then consistency is the one thing that really drives me crazy, because as we look across those 3 chapters, like I said, the approach by which you get to those final predictions or estimates of crashes by type and severity level is markedly different across virtually every chapter of the HSM. And so again, I guess if you're automating those processes, maybe that's less of a concern. But so for example, in this class though, every time I teach it, it's a balance of how much we get into the nuance here, because I think it's important that you understand the methods and how the methods are applied broadly, but I'm reluctant to have you understand and memorize the differences in each of the 4 or 5 different chapters that would present these different families. Because frankly, even from my perspective, it's tough to keep fresh what exactly how it's applied in each of the different chapters. Okay, so sorry, very long answer to the very short question you asked there. And so does that make sense? Okay. So like I said, we've got the 3 general facility types in the first edition. The supplement that was published subsequently focuses on interchanges. And then there are a series of other companion projects from the NCHRP, and some of the deliverables from those projects are basically draft chapters or sections of draft chapters that'll be in the second edition of the HSM. Okay. And so I talked a little bit about base conditions, and so you'll notice a lot of these base conditions are somewhat similar in nature to what's used in the HCM for operational analyses. So in the case of intersections, we're assuming all those intersections are right angle. As those intersections become skewed, we tend to see an elevation in crash risk. We also assume that there are no auxiliary turn lanes at the intersections. And I think I've talked about this a little bit before in this class, but I might be mixing this up with 849. Have I talked about turn lanes and trying to assess their impact from a safety standpoint? We've done several studies where we've found counterintuitive signs for some of these variables. So for example, we'd see intersections that have auxiliary left turn lanes experience more crashes. And I think that's a faulty premise generally. You install the left turn lanes oftentimes because you have operational or safety problems with those left turning vehicles and you want to pull them out from the through traffic. But typically, if we're estimating models that would have just major road and minor road traffic volume, one of the things we're not capturing there is the difference in turning movements across these different locations. And so if we're able to actually control for that, we would probably see a different result in terms of what the impacts of those turn lanes were. Okay. And so in any case, I just bring this tangent up in part. So this is calibrated such that these are all just intersections at 90-degree angles with no turn lanes of any type. We're also assuming there's no lighting present here. And then as you diverge from any of these cases, there are crash modification factors that again will allow you to scale up or scale down those estimates accordingly. Okay. Road segments, we've got quite a few more base conditions here. As in the case of the HCM, we're assuming 12-foot lanes and 6-foot shoulders. Roadside hazard rating, I'm not sure if you guys are familiar with that, but basically, this is a 7-point scale that was developed as a part of a prior research project where we're essentially qualitatively assessing the level of hazard posed by the roadside. So things like the distance of the clear zone, the frequency with which obstacles are near to the roadway. So, trees and culverts and various other features that are potential crash hazards. And so there's guidance in terms of how you would evaluate this on this rating scale. And so, like I said, it's a 7-point scale. And so we're basically assuming like an average. 3 is like an average-ish number. I guess a quick aside there, this is something we generally haven't tried to incorporate in any of the work we've done here in Michigan, in part because agencies, generally speaking, don't have robust inventories as to what the roadside hazards are like on a continuous basis across their road network. And so a lot of times that factor somewhat comes out in the wash. Similar to the HCM again, we're assuming small numbers of intersections and driveways, so no more than 5 per mile in this case. As you go beyond that, crashes tend to increase. We're assuming tangent, flat alignments, so no horizontal or vertical curvature, no rumble strips or passing lanes or two-way left turn lanes, no lighting or automated enforcement either. So basically the way these models were estimated, they were parameterized such that these base conditions were true in all cases. So if they had segments where passing lanes were present, as an example, they would estimate that as a binary indicator. And so if you think about the coefficient on that variable, when that condition is equal to 1, we'd estimate that beta, and that would tell us how much we would shift that line up or down from the base conditions, just like we've used binary indicators in the linear regression framework in 849. Okay. And the same thing is going to be true for any of these other features. So as we diverge from these base conditions, those models have essentially been calibrated such that when all of these base conditions are set equal to 0, or all these conditions are true, then you would match essentially with the baseline model from the HSM, and then you would tend to depart from that as you diverge from these base conditions. Okay. So Chapter 10, Chapter 11 are somewhat similar here. So we see the same general base conditions for intersections. For road segments, again, 12-foot lanes. So multi-lane arterials, we tend to see wider shoulders than we would on the rural 2-lane system. So 8-foot shoulders here, and also a 30-foot median. And as in the preceding case, we're assuming no lighting or automated enforcement present. And then similarly in Chapter 12, there are similar base conditions for intersections. We're again assuming no auxiliary turn lanes. We're assuming permissive rather than protected, or permissive protected, protected permissive. We're just assuming only permissive left turn phasing. We're assuming vehicles can turn right on red, and then again, no lighting or automated enforcement, nor any bus stops, schools, alcohol sales establishments near that intersection. Okay. And then for road segments, in this case, we're assuming there's no on-street parking, no fixed objects on the roadside, narrower median here as compared to the rural setting, so 15 feet, and then likewise no lighting or automated enforcement. Okay. And so as an example here, we can just work directly with that 4-leg signalized intersection model that was presented previously. So if we've got a roadway with an 11,000 AADT on the major road and 7,000 on the minor road, we can predict how many crashes would be expected. Oh, rats, should have changed that to 2021, apologies. In 2020, assuming similar traffic volumes. And so in this case, we're just applying this model directly, plugging in those respective traffic volumes. And so on that basis, then we would expect that a intersection with those volumes would experience roughly 10 crashes, or in this case, 10.1 crashes per year. Okay. And so we could use this same method to forecast how many crashes we'd expect to see at other 4-leg signalized intersections. And then we could use that either as an input for our network screening process, or as the basis for some subsequent design decisions, where we would use crash modification factors to see what treatments may help to decrease crashes from that baseline. Okay. And so to that end, I've used the term crash modification factor several times previously. And so what those CMFs are basically representing is they're a scalar that tell us how much crashes are going to change by if we implement some type of safety treatment. And so it's simply the ratio of how many crashes we'd expect to see with the treatment versus how many crashes we'd expect to see without the treatment in place. And so to that end, and I'm introducing some of the general nomenclature we'll see in the HSM. These SPFs are generally used to determine the predicted number of crashes at a given location. And so we start with the baseline safety performance function, and then in any cases where those baseline conditions aren't met, we multiply that baseline condition by these CMFs. And so at the end of the day, after you apply all those CMFs, the end result is how many crashes you would expect to see for a roadway with those select traffic and geometric characteristics. Okay. And so the next slide, I think, goes through an example here. And so we actually just had a kickoff meeting for our MDOT roundabout evaluation project yesterday. And so we'll be developing some similar CMFs here in Michigan, but in its current form, the HSM provides a CMF of 0.52 for total crashes where a roundabout is converted from a signalized intersection. Okay, so basically a bunch of data were collected nationally for these types of conversions. And so on average, crashes were reduced by 48%. And so we can use that information in combination with the preceding estimate to try to determine how many crashes we'd expect to see at the roundabout as compared to the crashes we would expect at that 4-leg signalized intersection. Okay. And so as we had noted previously, we've already applied that safety performance function that showed us a 4-leg signalized intersection with 11,000 vehicles on the major and 7,000 on the minor. Would experience 10.1 crashes on average. And so if we reduce those by 48%, we end up with 5.3 crashes at the end of the day. Okay. And so in this case, this is a very broad and very general conversion because there's a lot of nuance that comes in the roundabout design. So beyond this general CMF, we could also look at other CMFs that would relate crash performance at roundabouts to some of those different design parameters of interest. Okay. And so are you familiar at all with the CMF clearinghouse? Okay. So the FHWA maintains, I think this is contracted through the University of North Carolina Highway Safety Research Center currently. And so this is basically a website that details a very wide range. There's probably thousands, one of tens of thousands. There's a huge number of CMFs that have been developed here from prior research. And so North Carolina is under contract from the FHWA. They basically review the fundamental research reports and the journal papers that have introduced some of these CMFs, and then they apply a qualitative rating scale, basically a 5-point star rating scale based upon factors like how large was the sample that was used to develop that CMF, how rigorous were the methods, so did they use just the naive before and after design, did they use a control group study, did they use an empirical Bayes method, and there's a variety of other different metrics that are utilized there. And so this is essentially, it's viewed as like a one-stop shop to try to get any and all information you would want to help inform design decisions and safety forecasting generally. Okay, and so as you can see here, you can sort through a very large number of different categories. You can sort by keywords. It's got features. So a subset of these, so basically, I forget if they had anything that was 4-star and above, I believe 4 or 5-star, was actually incorporated into the first edition of the Highway Safety Manual. And then you can search by that constraint. You can search for those that aren't included, and that would include anything that's published subsequent to the first edition and so forth. And so, like I said, for each of those, you'll get estimates of what the corresponding CMFs are, and then the CRFs, and I forget whether I've used this terminology before or not, but CRF is basically just 1 minus the CMF. So this is telling us it's a multiplier of how many crashes we'd expect to see with the treatment versus without. And the CRF is just telling us how much crashes would be reduced by with the application of that treatment. Okay, so these are just complementary in nature. If you're experiencing 71% as many crashes, you're reducing crashes by 29%, obviously. Okay. And so, like I said, they've got star ratings applied to each of these. And to our preceding point about estimating models for very narrow subsets of crashes, there are also type-specific and severity-specific details provided here, as well as if that study was conducted on a certain road type or in an urban versus rural area. So you can get really far down into the weeds here. And from a DOT perspective or a practitioner's perspective, I guess one concern I have here is that it can be somewhat overwhelming. So if you just search for a countermeasure for, I don't know, say red light running, as we did in this case, we get a laundry list of different CMFs. And so then it can be a challenge just figuring out which of those is most appropriate. And so we've got a project ongoing with Ford right now where we're trying to automate this process to a degree. So basically go through the CMF clearinghouse and identify all the countermeasures that would be appropriate for certain roadway types in certain environments and certain crash types, and then try to automate all of that. So functionally, the way it works is we've got some network screening functionality that's been built in. And so we can identify lists of locations that are ranked by the relative crash risk. And then we're trying to build in some AI basically that would help to identify the countermeasures that would be most appropriate. Sounds really easy in concept. It's very, very nuanced. And so it's very challenging, short of going through and classifying each of these individual studies individually and integrating that as appropriate. It's just a real challenge. So just a practical concern I wanted to raise there. And so on the preceding slide, you noticed in those cases, we generally saw just single values for CMFs. There are also cases where rather than a crash modification factor, we see what's referred to as a crash modification function. And so in this case, this is basically showing us differences for lane width. And so here we basically see there's an interaction between traffic volume and lane width effect here. So at very low volumes, we don't see much of a difference in safety performance. So if you go from 12 all the way down to 9 foot, you only see a 5% increase in crashes. In contrast, as you get to higher volumes, and this should make sense intuitively, you're seeing a lot more interaction between vehicles. And so those narrower lanes introduce greater safety risks until you get up to specific volume levels where you're not going to see a lot of 2 lanes, rural 2-lane highways that are beyond these, and that starts to plateau out at that point. Okay, so you'll see different forms. And so again, these are all based on empirical research, so there are an infinite number of different ways these could be parameterized, but by some rationale or series of statistical tests, that's how they arrived at this specific fit or format for the CMF. Okay. And so again, what we're doing here in concept is we're applying these CMFs by the expected number of crashes before a treatment is applied to determine how many crashes would occur afterwards. One concern that arises there that's still kind of an important and emerging issue in the safety literature is what happens if you have multiple improvements. And so to that end, the way it's handled currently is that we assume these effects are multiplicative. Now, what happens there, if we're looking at introducing 5 different treatments, it's probably unlikely that if you applied all 5 of those treatments, you'd see the same effect for each of those. There'd probably be some diminishing returns here as we apply additional treatments. But as it turns out, that's a very challenging issue to try to address empirically when we're developing these regression models. And so there are a few studies that are currently looking at alternative formulations here, but this is still the way this issue is currently addressed in the current edition of the Highway Safety Manual. And so I just wanted to bring that to everybody's attention there. Okay, so we're assuming these effects are independent. That's probably a tenuous assumption, but there's not really a good consensus as to a better way to accommodate that, at least at present. Okay. And so just a few examples I'm going to quickly work through here to demonstrate the application of CMFs. And so let's say we've got a 3-mile, 2-lane rural highway. We've got a tangent section, no horizontal or vertical curvatures. We've got 12-foot lanes, 5-foot shoulders, AADT of 5,000 vehicles per day. And so we basically want to compare that existing proposed design to an alternative where we'd be using 10-foot lanes and 7-foot shoulders. And so if we assume everything else is the same, we're going to use those SPFs and CMFs to derive estimates of what the change in safety performance would be ultimately. Okay. And so the first thing we would do is we would take that baseline SPF and plug in our base conditions, which in this case would just be the traffic volume and length of that segment. And so, like I said, 5,000 vehicles, 3-mile segment. And so we'd expect to see 3.37 crashes per year, okay? And then from that, we would want to determine the appropriate CMFs. And so here we see adjustments for shoulder widths. And in our case, I believe we said we had 5-foot and 7-foot shoulders. Now what you'll notice here is that we don't actually see corresponding lines for 5 and 7-foot shoulders. What would you suspect were recommended to do in those instances?
Interpolate.
Right, so we're basically just using straight line interpolation, which is particularly easy if you're in either extreme range here, if you're in the middle. It's a little bit more involved, but you do know the slope of that line, and so you can use straight line interpolation as well to go between those respective CMF ranges. And so we're going to adjust our base conditions accordingly. And so from that preceding example, and just that 1.075 number, we had 5-foot shoulders, so we're halfway between those two lines essentially, okay? And so in that case, we would see an increase to 3.62 crashes per year from the 3.37 we saw previously when we had the 7-foot shoulders, okay? And so as we look at the lane width and shoulder width adjustments here, so we've already worked through the example for 12-foot lanes and 7-foot shoulders. And so if we look at, 12-foot lanes and 5-foot shoulders, if instead we look at reducing those lane widths from 12 feet down to 10 and increasing the shoulder width from 5 to 7, we see an increase in crashes as we reduce the lane width, and then we see a decrease in crashes as we increase the shoulder width. And so collectively, those two effects, when taken in combination, would give us a 21.6% increase in crashes on average, okay? And so we can apply that directly. And so in this case, we're basically just taking the ratio of how many crashes we would expect to see with those revised, the narrower lanes and wider shoulders as compared to the wider lanes and narrower shoulders. And so our change in crashes here is basically 0.47 per year, okay? And so in this case, that would be an increase in 0.47 crashes per year. And so this would give justification for the initial design we started with, where we had the 12-foot lanes and the 5-foot shoulders. Does that make sense? Okay. All right. I'm a little behind schedule for various reasons today. Do you guys have a hard stop on the back end? Okay. So it would be good to get through this. I was going to say alternately, I can just record this and post it to D2L, but we've worked through the empirical Bayes method the past 2 weeks. In the HSM, they've basically taken that same approach and they've kind of streamlined it and used slightly different nomenclature rather than having to memorize that pi is our expected number of crashes and lambda is the number of crashes we experience after implementation. We use slightly different nomenclature here, but the general setup is the same here. We're calculating a weighted average between how many crashes we're actually observing at a given location and how many we would expect to observe at that location based upon empirical data from a series of control locations, okay? And so you'll notice here the setup is the same, except like I said, the only thing that's changed here is basically the symbols and the terminology. And so our expected number of crashes is a function of what's predicted from the empirical equation and what's actually observed. And these weighting factors are analogous to the weighting factors that were introduced last week. And those are calculated using a factor that incorporates the overdispersion parameter that we had introduced previously. And we'll walk through that, I think, on the next couple slides here. So in the case of road segments, that weighting factor is calculated using this equation, which looks somewhat similar to what we had presented previously. So that weighting factor is a function of these different characteristics here. So first of all, the overdispersion parameter, and so just as we had talked about last week, that over dispersion parameter is giving us a sense of how much variability and or how much precision we have in those SPFs that have been estimated, right? And so the larger that over dispersion parameter, which last week I believe we introduced as alpha, K is just alternate terminology that's used in the HSM. And so the larger that value is, the less reliable that predictive equation is, okay? And so consequently, as our over dispersion parameter gets larger and larger, the denominator here gets larger, that weighting factor gets smaller, and as a consequence, we're giving less weight to that equation as a function, okay? Likewise, we're also giving less weight to the predictive equation when the number of crashes we expect to see is larger. And so all we're essentially capturing there is sites that experience more crashes, those estimates tend to be more reliable from year to year. And so regression to the mean is a lesser concern on high crash segments versus low crash segments, just given the inherent variability in crashes. And then likewise, the length of the segment also plays a role here. Now that's going to actually work in the opposite direction, because in this case, the longer the segment is, as that gets larger, then you're going to see that this term on the bottom tends to get smaller. And so we're giving more weight to the predictive equation in that case. And that's essentially just a function of how we incorporate that length into our regression equation, okay? And so otherwise, this is fairly analogous to what we had presented last week with the EB approach, okay? In the case of intersections, it's exactly as you would see here, except there's no length component. So it'd just be 1 over 1 plus K times the summation of the predicted crashes, okay? And so as an example, if we've got a road segment that's 1.8 miles in length with an AADT of 4,000 vehicles per day that's observed 12 crashes, we can then try to estimate an expected number of crashes based upon that information. And so the predicted number of crashes, we're just plugging in to that same equation we had introduced previously. And so we plug in our traffic volume. We're provided with what the over dispersion parameter is that corresponds to that equation. And I should note here, when we look at those SPFs, those are generally presented on a per mile basis. And so that's where I had introduced that offset term. So if you've got a 3 mile segment, you would just multiply this estimate by 3, or in this case, the 1.8 mile segment, we just scale that up by 1.8 accordingly. And so under a roadway with 4,000 vehicles per day AADT, we'd expect 2.41 crashes per mile per year. Since our segment's 1.8 miles, we'd expect 4.34 crashes per year. And then down here, we're just plugging in, again, our over dispersion parameter K is right here. We have 1 year of data here and 4.34 crashes per year. Divided by 1.8, which is again our segment length. And so our weighting factor for this specific site is going to be 0.46. And so that's the weight we applied to what's given by the predictive equation. We add that to the number of crashes that were actually observed at those sites. And so then our net, then our expected number of crashes is 8.48 per year, or 4.71 per mile per year, okay? And then if we want to calculate the standard deviation, this again is analogous to how we had calculated sigma last week. So this is just 1 minus that weighting factor. And then this is the expected number of crashes, which would have been similar to pi in last week's terminology. Does that make sense? Okay. All right, we can apply the same general approach with 3 years of crash data. And so the same site, same characteristics, except instead of having 12 crashes during 1 year, we now have 12, 7, and 8. So 27 total over a 3-year period. Everything else is as presented previously. And so just working through in an analogous manner here, we're now expecting to see 13.01 crashes over the 3 years. So we're just taking that annual estimate and multiplying by the number of years in our analysis period. Now, with that increase in our analysis period from 1 to 3 years, you'll notice our weighting factor here has changed considerably, right? Because this 1 is now replaced with a 3. Everything else is essentially analogous here. And so then as we work through here, our expected number of crashes is now 23.92, which is just the weighted average of the 27 we experienced and the 13 that were predicted by the regression equation. Okay. And likewise, we can take that standard deviation and we could construct a confidence interval on that expected number of crashes as well. Okay. We can take that same segment and we can integrate crash modification factors directly into the process here. So this is just building upon the preceding example again. And so in this case, the only difference is that baseline predictive model, instead of being our normal base conditions, we've got some sort of change that requires us to scale those crashes up accordingly. And so as we look at this, the only thing that really changes here is we've got a slight adjustment here, a slight increase in the number of crashes that are predicted. And so as a consequence of that, this weighting factor has been reduced very gradually. And then you see what the carryover effects are then on our expected number of crashes and the standard deviation of that estimate. Okay. And I think I might have, I think this is the last one. Another thing that arises frequently is we're combining multiple segments, and each of those segments has slightly different characteristics. And so combining those estimates in order to come up with either for a larger segment or for the homework assignment where we're looking at a statewide rumble strip installation program, we'd use the same type of approach here generally. And so in this case, we would go through and we would calculate the predicted number of crashes for each of those individual segments. And then it's simply additive. And so we would sum those respective quantities together. And then when we come down here to look at the actual estimates here, we would also, the only substantive difference here, our over dispersion parameter is the same. In this case, we've got the 3 segments, and so we would look at the lengths of those individual segments here as we go through. And on the preceding slide, or actually it shows right here. So the segments are 0.1, 1.2, and 0.2 miles in length. And so that's the total segment length of 1.5 miles. And likewise, this is the total number of crashes across each of those segments. Okay, so we're just basically summing up the crashes. We've got 2 years in total. That's why the 2.527 compares to the 5.054 here. This is our corresponding weighting factor. And so as we've done previously, in this case, we're assigning that to the total crashes we've experienced on all of those segments collectively. And so from there, we end up with our estimates of the expected crashes and the associated standard deviations. Okay. And so these are all just basically, we're building on the same general underlying framework that's been introduced previously for the empirical base. Okay. And so for this week's assignment, and I did remember your question, Jordan, so you can feel free to ask that after I click through these 2 slides. You've previously worked with the cable barrier data set, and so I tried to find another data set to work through, and probably the best example we have is from the statewide rumble strip installation program that we helped MDOT to evaluate more than a decade ago now at this point. And so we've got data for 4,000 miles of 2-lane highways. And we know that rumble strips were installed across those segments between 2007 and 2009. And so they put center lines everywhere. They put shoulder rumble strips where there was a sufficient width that they could accommodate both the center line and the shoulder strips without, the concern there is if it's too narrow, there'd be a lot of incidental contact, and motorists don't like that, and nearby residents don't like that. And so over that 3-year period, roughly 1/3 of those installations occurred each year. And so the task in this assignment is to basically use the 3 general frameworks we've talked about up to this point. So naive before and after evaluation, a cross-sectional evaluation, and then an empirical Bayes evaluation. And I can help walk you guys through. We probably don't have the time today, but I'll just put together a short video. We can use SPSS to estimate negative binomial models in order to work through any of these three general approaches here. And so at the end of that analysis, we basically want you to assess the differences. And interestingly, one thing you'll find here is that for this large of a program where we're looking at 4,000 miles, you're not going to see super pronounced differences. Had we looked at just a 50-mile subset, we'd see a bit of a difference there. But we're going to see the same general effects, but there will be some variation. And you can think about why we're seeing the differences that we're seeing across those three different approaches. But the data itself includes information. We've got a segment ID. We have individual years of crash data. We've got a series of dummy variables, whether or not we're in the post-installation period, so i.e. are there rumble strips present or not. Oh, sorry, I said that backwards. So that we've got a variable. So we've got, I believe the way it's set up, I think I pulled 3 years of data before and 3 years after, but we might want to double check that. And so we have data for the post-installation period. We have data as to whether or not centerline have been installed only, or centerline and shoulder have been installed. So we could look at estimates of reductions in crashes with just the centerline versus the centerline and the shoulder. We've got traffic volume on an annual basis, segment length, and then I think you guys are somewhat familiar with the way we addressed horizontal curves in this case. So basically, we're just looking on those individual segments, what percentage or proportion of that segment has curves with radii of various ranges, okay? And we also have data as to whether or not passing is restricted or prohibited on the segments. We've got lane and shoulder width, various other characteristics relating to geometry, and also some weather condition information here. And then we also have a very large amount of data that details the crashes in our data set, and that includes total crashes as well as our target crashes, which in this case would be lane departure. And so these crashes were identified basically using a series of codes from the crash report forms as well as the crash report narratives. And so we basically manually reviewed every one of these crashes to figure out which ones of those would potentially be the types of crashes that would be impacted by rumble strip installation. Okay. And so the big task for this week is to determine how effective that program was using each of the three methods that we've talked about previously. Okay. Does that make sense? I don't know in all that talking if I answered your question, Jordan, or if it still remains.
One question was, is there a specific safety performance function? But it sounds like we're determining that for the use in this project.
Yeah.
My second question was, is a cross-sectional evaluation, is that just the control group, or is that a different?
It's a slight variation on the control group. So the cross-sectional evaluation, we basically we use that most frequently. I think I use the example of the installation and evaluating the impacts of signage as an example. And if you don't necessarily know when that treatment is installed, you would estimate a regression model that includes all of your sites, and then you would just have basically an indicator variable that discerns whether or not the treatment has been applied. And so you would just, in that case, we would just estimate a dummy variable for the fact that rumble strips have been installed. And then based on that parameter estimate, that would tell you what the change in crashes are as a function of the rumble strips. Does that make sense? Okay. And then I'm trying to think if there's anything else about this data set that you should be aware of. No, I think it's pretty straightforward. I guess to your initial point there is flexibility in terms of what that SPF or SPFs that you estimate would look like ultimately. And so, yeah, like I said, just let me know if you guys have questions as you work through it, but I'll plan to put together a quick tutorial in SPSS. It's fairly straightforward to estimate this family of models using the same approach we've done with the linear regression stuff in 849. So, other questions?